So, okay, next we have Suprabh. He is from IMSC, of course, and he'll be telling us about sterile neutrino searches with a deuterated liquid scintillator.
Hello everyone, the topic of this talk is sterile neutrino searches with a deuterated liquid scintillator. This is the outline of my talk. So I'll basically start with introducing, very briefly telling you about what the short baseline anomalies are and why they hint towards the existence of sterile neutrinos. Then I'll talk about what two-flavor neutrino oscillation probabilities are. After that, I'll talk about deuterated liquid scintillator and what kind of sterile neutrino sensitivities are possible with them. And finally, I'll conclude with the challenges that we're facing with estimating the background events. Okay. So for people who don't know what neutrino oscillations are, so neutrinos may start as some flavor, and when they propagate over a certain distance, if you detect them, the flavor changes basically. So a neutrino which was produced as a nu E can later be detected as a nu mu or a nu tau. So that's a very simple description of neutrino oscillations. The typical neutrino oscillations that we observe require two mass square differences, which essentially explain as the solar oscillation anomaly and the atmospheric neutrino oscillation anomalies. And the mass square differences that we require this for explaining those anomalies do not fit with some of the anomalous results that we are observing at certain other baselines. So in other words, the baselines, which is the distance between the source and the neutrino detector, for these experiments is too small to let neutrino have enough propagation time or distance in order to evolve into certain other flavors. So what are these anomalies? So you have, to begin with, a nu mu flavor, and you have a certain expectation of the backgrounds, which are shown by these green and the red patches. And then you observe, when you look for the nu E driven events, you're seeing a lot of excess. So here, basically, this blue patch shows you the best fit with the, if you consider that there is neutrino oscillations happening between the nu mu and the nu E flavor. So this was one experiment which ran in nearly around 2000, and later to check those results, another experiment was planned in the US, and it also is observing similar events where you have a nu mu or a nu mu bar to begin with. So you should not expect any electron-like events in the detector, not above the expected backgrounds. But what you observe is that you have a lot of anomalous excess of electron-like events. So yeah. There's this another baseline, there's this another anomaly which I'm going to talk more about. So basically what you have is that you have as you all know, in nuclear reactors, we have nu E bars coming out. And so if those nu E bars propagate for substantial distance, then they may oscillate into other flavors, which is to say that the probability that the nu E remains as a nu E may start deviating from 1. And in the standard neutrino oscillation scenario, we expect that to happen only when the neutrinos have traveled roughly around 1 kilometer. So if you see this 3 neutrino curve, which represents the standard model of neutrinos, the oscillation or the P nu E to nu E will start deviating from 1 only after they have reached 1 kilometer. But if we have additional sterile neutrino, then those oscillations can actually kick in at very shorter distances of the order of 10 meters away from the reactor core itself. Okay, so this is the neutrino anomaly, and the most economical way of explaining these anomalies is to just add another another species of sterile neutrino. And since we know that the standard model can only accommodate 3 electroweak neutrinos, so this additional neutrino must be a standard model singlet. So yeah, so conventionally we call these neutrinos as sterile neutrinos, and so sterile neutrinos cannot be detected through any of the particle physics interaction, and the gravitation is also, their masses are also too small to have any kind of gravitational effect. The only way to sort of observe this is indirectly via mixing with active neutrinos. So we just call this model as 3+1, and in order to explain the previous anomalies, you require the neutrino masses, the mass of the heavier sterile neutrino to be around 1 eV. Just for a reference, the current constraint on the lighter neutrino masses is of the order of 1 over 100 EVs, roughly from the Planck data. So this is 100 times larger. Okay. Okay, so so this is a simple expression for neutrino probabilities in two flavor, which is what we are concerned with for any result that I show in here. So basically there are only one mass square difference or only two mass eigenstates that we need to worry about. So it's a very simple expression where you have a new alpha being E mu or tau to start with, and when it propagates over time, you have a simple Schrodinger-like wave equation time evolution for that, and then you later just superimpose with the final flavor that you see. And in a two flavor scenario, that expression is simply this, where a nu e, where a neutrino which is born as a nu e can later be detected as a nu e with this probability, and it may oscillate to something else with this probability, and you can see that the sum of these two probabilities is just 1. So here we have sensitivity to only two oscillation parameters. One of that is the effective mixing angle, which is the mixing between the mass eigenstates and the flavor eigenstates. And there is only one delta m square we need to worry about, which is the mass square difference between the heavier eigenstate, the sterile neutrino, and the lighter ones. So this table here roughly gives you the kind of mass squared sensitivity that we have with the reactor baselines and energies. So these are the ones that we are concerned with. If you are at 1 kilometer, you will be sensitive to the solar, the atmospheric scale. If you're at 100 kilometers, you'll be sensitive to that solar scale. At very short distances, we may have sensitivity to 1 over 10 or roughly 1 eV square mass square difference. Okay, so our focus is to see what a deuterated liquid scintillator can tell us about the sterile neutrino searches with a reactor neutrino source. So as an example, we consider this reactor experiment, which is nuclear power plant, which is situated in Kudankulam in Tamil Nadu. And the power of each unit is 3 gigawatt thermal. Here I have shown the neutrino fluxes that come out from the nuclear power plant. Here you have the 4 isotopes. And typically these isotope fuel composition evolves with time, but this is the typical ratio that we have. So you can see that the fluxes are exponentially falling with time. And yeah, so why a deuterated liquid scintillator? So one of the main reasons to use a deuterated liquid scintillator instead of a typical liquid scintillator that the neutrino experiments employ is that it has sensitivity to both the charge current and the neutral current events. And India is one of the largest producers of heavy water, so having a deuterated liquid scintillator is not a very difficult job for us. And so the pluses in this setup is that the neutral current events can provide additional sensitivity to the sterile neutrino oscillation parameters, and which is not possible only with charge current events. But as we see, it comes with its own set of challenges, especially with respect to background events. And just to give you a perspective, it was because of observing the neutral current events that Snow experiment could conclusively establish that neutrino oscillations, neutrinos are actually, the total number of neutrinos is conserved, and it's just that they are oscillating from one flavor to another, for which the Nobel Prize was awarded in 2015. So these are the cross sections for deuterium. So here I have the total cross section as a function of the neutrino energy, and this is shown for both the charge current interaction and the neutral current interaction. And if you compare this cross section plot with the previous exponential falling flux plot, if we just simply multiply them, assuming that none of the neutrinos are oscillating, then you would see that the typical peak that would happen is around 4 or 5 MeV. So that's that's in the that's when neutrinos are the particles which are being detected, which is not possible. So instead, what you see is the visible energy, which in the case of charge current events is a positron, and in the case of neutral current events is a proton. So in the case, so these are the typical differential cross sections. So some of the energy is taken up in order to dissociate the deuterium, and then later and most of the neutrinos in the case, most of the positrons in the case of charge current then would peak at roughly around 4 MeV for a 8 MeV true neutrino. And then, so this is the profile for charge current. In the case of neutral current, it's different because the daughter neutrino particle takes away most of the energy, and the remaining energy is distributed between the proton and the neutron, and they typically peak at very small energies, roughly around 200 keV. Yeah, so these are the charge current interactions. In the case of, so these are the neutrino interactions. In the case of charge current, you would have a nu bar which hits a deuterium, and then you have a E plus, a positron, and two neutrons in the final state. The positron would give a Cherenkov light signal, and these two neutrons then act as a tag. So you observe two gamma ray lights. So this is a very clean signal. So you have a prompt and then two delayed events. In the case of neutral current, this nu bar would just dissociate. So you have a nu bar which takes away most of the energy. You would get you would get the scintillation light due to the protons, and then this neutron can as a tag, acts as a tag for the neutral current interactions. If you did not have deuterium, in other words, if you don't have this neutron, then you don't get this tag, and it's very difficult to observe this interaction without a deuterated liquid scintillator. Okay, so these are what the probability plots look in the case of the baselines and the energies that we are concerned with. So in the red curve shows you the disappearance probability where a nu E is oscillating to a nu E, and the total flavor. So this essentially represents the probabilities that a nu E could oscillate to a nu E or a nu M or a nu tau. In the case of 4 flavor, and in the case, the black line represents the nu E, the electron disappearance probability in the case of 4 flavor. So this essentially, so if you see this equation here, this is essentially 1 minus the probability that nu E's are oscillating to some sterile flavor which we cannot observe. And if there is no sterile neutrino, then this sum is going to be equal to 1, which is the case for 3 flavor. In the case of 4 flavors, then this again is essentially equal to PEE, because we are in a 2 flavor assumption where PE mu and E tau are very small. So I mean that is visible, that is clear with this through this feature here, where the red line and the there's essentially no difference between the red and the blue curves. So some of the few good things about this channel is that this does not have sensitivity to the matter effects or the mass ordering or octant or CP violation. So any deviation from that, what you see from the expected, can cleanly be attributed to either an effective mixing angle with the sterile sector or a mass and a mass square difference. Okay, so here I'm showing some events plot. So these are the total number of events as a function of the visible energy. For the kind of power that we have with the nuclear setup, the nuclear power plant, we expect roughly 500,000 events for the neutral current and 300,000 events for the charge current. The neutral currents even essentially peak up at this very small baseline, very small energies, and the charge current more have, they are spread out up to around 5 MeV. And here on the these plots below, I'm showing the ratio of the oscillated over unoscillated event rates. So any deviation from one signals an oscillation kind of feature, and you can see that for a 30-meter baseline, both with very small values of the mixing angles, 5 degrees and 10 degrees, you'd see oscillation features due to both mixing angles as well as mass square differences in both the charge current as well as the neutral current channel. So modulo any of the uncertainties in the flux normalization, the cross sections, etc., the physics itself is sensitive to the oscillations in both the channels, charge current and neutral current. So yeah, okay. So these are the final sensitivity plots. So for comparison, I've shown the Dirac excluded region in the delta m square 4 1 sine square 2 theta 1 4 plane. What is on the left is the region that is, sorry, this is wrong. So yeah, so what is on the right is the region that is excluded, and this whole region is allowed. So so you can see that even with much lesser statistics, the results are quite comparable to the existing constraints that we have in for excluding out the sterile neutrinos through Dirac. Yeah. So, but one of the things that I did not talk about is the challenges that we face with respect to the background events. So, so the main problem comes with cosmic muons, which lead to the production of neutrons, which so if we do not know what those numbers are, it might be difficult to resolve between the signal and the background. So that's the very, I'm going to put that in a very simple way. Yeah, so yeah, that's all. So to conclude, so one of the good things about DLS is that it has sensitivity to both the charge current and the neutral current events. And the sensitivity that we are that we can in principle have with a deuterated liquid scintillator is comparable to the present constraints that we have with sterile neutrino scenarios. And we still have to work on the backgrounds to get a more final understanding of the sensitivities. Yeah, thank you.